have this paper, which is a variation of a preceding one I gave for the preceding meeting. I try to, in some extension, to Laguerre-type population dynamics using a parameter. The idea is related to, oh, moment. It's not working. Oh. It's not working.
Maybe if you go to, it's LibreOffice, huh? So if you go to the presentazione, maybe.
But the problem is it's impossible to see.
But if you go to presentazione, maybe?
Visualizza presentazione, but it's not here. Oh, okay, this one. Oh, yeah. Okay, now it's okay.
I understand a little bit of Italian.
Okay, so we show the short introduction about the models of Laguerre-type models of population dynamics. And after we introduce the pseudo-exponential function and the parametric Malthus, Verus, minimum threshold, and Volterra-Lotka models, and show some examples. It is a joint article with Diego and with Paolo Natalini. Okay. Mathematical models describe the evolution over time of number of individuals in one or more population have a long history, which can be found described in the Nicolas Bacher text, A Short History on Mathematical Population Dynamics, Springer Verlag 2010. Many scholars have dealt with it, beginning with the pioneer working of Malthus dating back to 1798, which was based on the exponential model. Subsequently, 1838, Pierre Verhulst proposed the so-called logistic model, which takes into account the fact that the growth cannot be unlimited, since it depends on the resources of the environment in which it takes place. Many variants of these initial models have been proposed, among which the one that predicts the existence of a minimum level below which the population tends to become extinct. This actually happened since many species have disappeared. Another significant study refers to the interaction of two populations fighting for survival in the same environment. This is the famous prey-predator model that takes back to the studies of Alfred Loika and Vito Volterra in the 1920s. The model was validated in 1945 by Patrick Leslie, who was able to view statistical data on hare and lynx population levels cycles in the archives of the Hudson Bay Company in Canada. More recently, we have used, instead of the classical exponential, the Laguerre-type one, which is an eigenfunction of the Laguerre-type operator, a particular case of hyperbessel-type operators considered in operational calculus by Ditkin and Prudnikov. Bessel-type differential operators of arbitrary order n were introduced by Dimoskin in 1966 and later called by Kiriakova hyperbessel operators because they are closely related to the eigenfunction of the called hyperbessel by Delroux in 1953. So this is a remark due to Virginia Kiriakova, who, reading our preceding paper, introduced and then this to meet this kind of preceding literature. The fractional Laguerre-type population dynamics model have been considered in the preceding article, where we have shown how to compute recursively the coefficient of the relevant solution expanding in fractional power series. It was proven in the a paper in which joint paper with Pino Dattoli. The idea is essentially by Pino. The Laguerre operator can, with the relevant eigenfunction, which is the Laguerre-type exponential, admit a parametric extension of the type derivative times derivative plus m derivative with respect to t, where m is a positive integer, whose eigenfunction is called, written in this way, a sub 1, comma m of t, is the sum t over power k divided by the factorial of k times the factorial of k plus m. This allows us to study parametric polarization dynamics models depending on the parameter m, which could be used in order to fit the real data. So the idea is the classical theory of population dynamics model depends on the choice of the exponential. Every time you find a different type of exponential, you can reconstruct all the theory, all the models, Malthus, Verhus, and so on, Volterra, Lautre, and so on, changing the exponential, which is the basis of the theory. In this lecture, you use this kind of exponential. This starts with an idea because some time ago I received a paper by Abhishek Mishra. We introduced a set of pseudo-exponential functions defined in a similar way. This exponential here is not a real exponential, because if you with respect to the ordinary derivative, because if you use the ordinary derivative applied to this function, it is not reconstructing the same function, but the function is the parameter shifted by 1. So this is a pseudo-exponential function. But using this also was already known, because is a special case of the Mittag-Leffler function studied by Brabhar, which is written in this way, which also have an extra parameter gamma here, which is gamma sub k, denotes the Pochhammer symbol, in disappearing in this position. But if you take gamma equals 0, so this equal 1, and the parameters alpha and beta equal 1 and m, you reconstruct exactly the function by Mishra. So we have to, in what follows, use the function with this symbol. This function introduced before, but according to the paper by Dattoli and myself, old paper in which we used the Laguerre-type exponential, this function is a real exponential, not with respect to the ordinary derivative, but with respect to this kind of operator. Using this kind of operator, if you apply this operator to this function, you just reconstruct the same function. For every constant a, you find the constant times the same function. So this is takes the place of the exponential. I use this exponential type function instead of the classical exponential. You can reconstruct all the theory of the population dynamics models. Starting with the Malthus case, the Laguerre-type Malthus model, this is we have studied in past time, using diciamo simply the Laguerre-type derivative. The Laguerre-type Malthus model is written in this form. This is the problem with the initial condition P of 0 equal P sub 0, and then derivative P of 0 times R. R is the growth rate, a suitable constant, positive constant. The solution is given by similar form of the classical case. Instead of the exponential, we have the Laguerre-type exponential, a sub 1t defined in this form. So in some sense, there is a perfect correspondence, which depends on the isomorphism we have introduced in the paper by Pino and myself. The Laguerre-type parametric maltose models runs in this form. Instead of the Laguerre derivative, we use the operator, the Laguerre derivative plus m, the ordinary derivative, applied to P of t is R, the constant R, times the same functions. This is the equation, and you have to assume the initial condition P of 0 equals P sub 0, and the derivative 1 over m plus 1 R P of 0. Of course, with m equals 0, it becomes return back to the Laguerre-type model, not parametric in this case, of course. So the idea is to find the solution in this form. You use the sum a sub k, the indeterminate coefficient, times this power divided by the 2 factorials. The solution of the problem is given by m factorial p of 0 a sub 1 m, so the eigenfunction of the parametric operator, Laguerre-type parametric operator, computed in the R times R. This is a classical case, because if you put m equals 0, you recover the preceding situation. The proof is simple. Writing the solution this form, you apply this in solving the equation, and you find, repeating the proof in the theorem, we have not written explicitly, but this is just a computation. If you apply this operator, here, applying first the first derivative, this is also the derivative, and starting from 1, and applying this, multiplying by t and applying again the derivative, you find this sum. And in this sum, k plus m divided by k plus m factorial gives back k plus m minus 1. And starting from 0, you recover the initial function. So the question writes in this form, and comparing the coefficient, you find that a sub k plus 1 is R times a sub k. So you find a sub k is R to the power k a sub 0, and then you find the solution with the initial condition are satisfied by simple inspection. And the solution is exactly in the form we have predicted before. So the series is, like in the classical case, is converged in all the plane. So the result of this theorem can also be obtained by observing that the correspondence between the ordinary derivative and this operator, taking into account the inverse operator, the primitive, can be framed in the so-called monomality principle, Lattoli principle. But it is a principle of the second kind, in which there is only a slight difference. And this is recalled in the paper by also Pino and also myself, and also a paper by Iliko, Tagvelix, and myself. So the logistic case, this is the Laguerre-type Vercruz model, in which we have the Laguerre-type derivative applied to the function, and R is the constant and before. K is related to the environmental resources, the maximum possible resources. So this is the classical situation applied to the Laguerre-type case, and you find that when P tends to decay, so the ratio tends to 1, and so this equation tends to 0. Expanding the solution in this form using the expansion similar to the exponential Laguerre-type exponential, you find this result. The coefficient of the expansion for the solution on the Laguerre-type Verhulst model satisfies this recursion. So you can construct by recursion the coefficient of the solution, and this was validated by in the preceding paper of ours. In this case, we have the Laguerre-type parametric Verhulst model, in which instead of the Laguerre derivative, you use this operator, and the situation is similar. The only problem is that you have to assume this different initial condition, P of 0 equal P sub 0, and the derivative is 1 over m plus 1 r times P0, 1 minus P0 over k. And you recall when m is equal 0, you can return back to the preceding case, to the case of Laguerre-type, not parametric, of course, Verhulst model. In this case, the solution of the parametric Verhulst model is given by this equation, which extends the classical case, in which for m equals 0, you find the case in which this is the Laguerre-type exponential. In order to check this result, we expect the solution in the form of the equation 8. The equation 8 is the equation in which you find this form, this expansion, with this power divided by the two factor with in unknown coefficients. After performing the computation in the equation we have we find the coefficient of the expansion rate for the solution of the parametric Verhulst model satisfies this recursion. In case when k minus n sub m denotes the Pochhammer symbol. In case when m equals 0, you recover the preceding situation in which the operator is just the Laguerre-type operator. This example made by Diego using Mathematica, assuming m equal 2, r equal 1, k equal 2, and putting p sub 0 equal 1, the solution of the parametric Verhulst model is given by the expansion, which I've seen before, whose coefficient are reported in figure 1. This is just the first 20 coefficient of the solution. The graph of the solution using this coefficient compared with that obtained using a predictor corrector method is reported in figure 2, in which you see that the two methods, with the method using the recursion of coefficient and the other one in which you use the predictor corrector method, are exactly the same up to in this interval, of course. So, in the preceding article, we used the numerical method for finding the solution of the Verhulst model, but in this case, we use the recursion of a coefficient, which seems to be more convenient.
It's like a rare.
The minimum threshold logistic case, Laguerre-type minimum threshold logistic case is shown by this equation, which is the Laguerre-type derivative, and the initial condition are P of 0 is P sub 0. The derivative is some gamma is a positive constant, M capital M represents the minimum number of individuals below which the extinction of the species occurs. Since in this case there is a time, tau, for which P of tau becomes zero. So the population is extincted. The equation is written in this form, and the classical theory applied to the case of the Laguerre-type derivative gives a solution in this form. So this is the Laguerre exponential, the power divided by the factorial raised to the square, of course. And the solution is this. For t going to the infinity, P of t tends to k. It is possible to prove that if P0 is less than m, the positive time occurs in which P of t equals to 0, so the extinction occurs. The curve of the logistic type is obtained using this operator, and you have only to put the initial condition in this form. P of 0 is P0, and the P prime 1 over m plus 1 in this P0 initial values here and here. And considering the solution we saw the expansion we have shown before in equation 8, the solution of the population minimum threshold is given by this equation. And in this case, it's similar. Instead of the Laguerre-type exponential, we have to put the eigenfunction of our operator, which are given by the expansion in which ek is equal to 1. So, in order to check the solution, we expand the solution in this form. After performing computation, we find this result. The coefficient of the expansion for the solution of the parametric volumetric population logistic minimum threshold model satisfies this recursion, where k minus n sub m denotes the Pochhammer symbol. A graphical example computed by Diego also, assuming m equal 2, r equal 1, k equal 2, and putting p of 0 is 1, the solution of the parametric logistic minimum threshold model is given by an expansion in which the coefficients are reported in the following table up to the order 20. And the graph compared with that obtained by using a predictor corrector method is reported in this form, in which the two curves are cannot be distinct, so are completely considered. The Volterra-Lotka. This is the classical Volterra-Lotka. A family of two species fighting for survival in a given environment. The environment's resources are thought to be unlimited for the prey's growth, while their development is limited by the presence of the predators that feed on them. Denoted by x of t, capital X, and the number of preys at time t, and y of t, that of predators, and it's assumed that in the absence of the predator, the number of prey grows according to the Malthus model, while that of predators in absence of prey decrease according to the same law, with the sign minus in this case. The space living of predators is increased whenever in the encounter between a predator and a prey, it's occurred that the predator succeeds in finding the prey. Conversely, the number of preys corresponding decreases in such an eventuality. Accordingly, the phenomenon satisfies the system of differential. This is a classical theory by Lotka and Volterra. And the Lotka-Volterra system is not elementarily integrable. It is therefore traced back to the phase plane, standing R a function of y. In the phase plane, the curves are closed curves around an trivial equilibrium point, which is given by x r over beta and y s over gamma. The In that point, the number of predator and prey remains constant over time. The case of the Laguerrian-type model is obtained substituting the derivative with the Laguerre-type derivative. The situation is similar. But in this case, we find an approximation of the solution, expanding the solution in this form. Capital X of t, which is similar to the Laguerre-type exponential with coefficient a, and y of t, this guy with exponential b. The solution is obtained by using the following recursion for the coefficient, which is written here in equation 13. The case in which we use the parametric type is similar to use the new operator, d of this is Laguerre-type plus m of d of t. And the solution is the couple of functions which are written in this form with the coefficient a and b of k of this. And the theorem we have found, and the parametric Volterra block model is obtained by following recursion, which like ak and bk coefficient are given in this form. A graphical example is this one. Assuming m equal 1, r equal 1, s equal 1, beta equal 2, gamma of 2, putting x of 0, 0.5, and y of 0, 0.75, we find the coefficient up to the 50, plus 50 coefficient of a and b. And the curves of the solution compared with the approximation using predictor method is shown in this figure. A conclusion, a Laguerre-type operator containing a positive integral parameter which behaves as an exponential with respect to its eigenfunction was used to extend some classical population dynamic model of the parametric to the parametric case. The analytical graphical results shown with by help of the computer algebra system Mathematica confirm the possibility of using such model in which the parameter could be used for a bit better fit of real data. An extension to the fractional case is also possible. And it is also already have been done, but it's not trivial topic. As a matter of fact, in the fractional case, using this kind of fractional operator cannot be obtained simply substituting the factorial with respect to expression using gamma function in the eigenfunction of the operator ordinary, not fractional, but requires a more deep analysis. The substantial difference of this type of eigenfunction that had to be used results in a greater complexity of the recurrence formula that allows calculation of the coefficient of the Laguerrian solution. As a consequence, these results will be published in a different paper. And this is a list of the first one reference are classical. Important is the Baker short history of mathematical population dynamics. It shows there some article by ourselves many years ago using Laguerre-type special function. And the important the paper by Datoli, and this is the paper 8 in which we introduce this Laguerre-type exponential. And this is the paper suggested by Virginia Kiliakova and the paper by Michigan, and so by Pravkar, and so many thanks to